I realize that my talk is a bit of an outlier here in this series today, and so it's my job to explain to you also a little bit the background of quantum physics, and also a little bit about quantum computing, and hopefully we get also to the control applications and the stochastic control application. Okay, so quantum. The reason I'm working on the quantum stuff is that I hope that quantum physics is going to be a resource, quantum phenomena, a resource for computing, that you can do something more with quantum that you cannot do classically. And the famous property of quantum mechanics is the so-called superposition principle, that a physical system can be simultaneously in multiple states. This is famously explained, exemplified by the Schrödinger cat that is both dead and alive. Now, of course, the quantum systems that we have are not as big as cats. They're much, much smaller. But you can have qubits that can be in multiple states at the same time. So you'd have a classical bit is either 1 or 0. A quantum bit is 1 and 0. So it's something that is really a mind twist. If you have many bits, of course, they can then be in all these superpositions. So n bits would be 2 to the n possible states. And you can then process all these 2 to the n possible states simultaneously and get therefore exponential speed up in your computation in your device. Instead of having one input moving through 2 to the nth inputs go through at the same time. Of course, that's the dream, but then to realize is quite another story. So the way that I want to talk about how to use this is that basically that you take. So one way to understand how to do that is that you say, okay, I want to have a classical probability distribution, say Q of S, where S is a bit string, and map it onto a quantum state. And then if you were able to do that, make such a device in which the quantum state is represented by this wave function, it would mean that if you would measure, do a measurement on that quantum system, you get an output, a certain bit string, with a probability proportional to the square of that wave function. And so you would have implemented a sort of an independent sampling method to sample from a given target distribution. Now, if you know anything about sampling, sampling is very hard, and to get independent samples from any given distribution is a very hard problem. And so this is one thing that you could do with such a quantum machine. Okay, now there has been talking a lot about quantum advantages, and so yeah, so quantum advantage is a notion that the quantum computer has to be strictly better than the classical computer, because otherwise, why bother, right? So. And the quantum advantage, is often formulated in the complexity of the problem. So you have the problem of the space of the set of polynomially solvable problems. You have the NP class, that is solutions are verifiable in polynomial time, and then there is the quantum problems, and one of these quantum problems is problems that can be solved in bounded quantum polynomial time. So this is a probabilistic notion that you get a correct solution with a certain probability, for instance, 2/3. And if you then repeat it many times, you get a good solution. So and then it's thought that this class of bounded quantum polynomial, that it extends beyond the class of P problems, and so that there can be some interesting examples. And the most famous one is Shor's algorithm for integer factorization. So integer factorization, if I give you 15, I have to get it to prime factors. It's 3 times 5. If I give you 91, it is 7 times 13. And now I give you this number with all these digits, and you have to find the 2 prime factors. And this is a hard problem. And the fastest classical algorithm scales as e to the n, where n is the number of bits of the number, and the Shor's algorithm reduces that to polynomial time. There's other examples, but so this here you see a clear example, Shor's algorithm, and this is driving basically the whole quantum computing industry, because Shor's algorithm is behind crypto, about encoding secret how do you say security, security of message passing over the internet, and of course that's very important for banking. And so there's a lot of money behind this, that because if you have a quantum computer, you can basically solve, you can solve these codes in polynomial time. And so all the currently used commercial encoding systems would be useless. And so there's a whole industry, so there's a lot of interest in this. But in order to get to this, to implement this algorithm is actually not possible at the moment, because you need a quantum computer. And we don't have a quantum computer that can do this kind of thing. So here is this is an excerpt from the IBM roadmap that is updated every year, and we're now 2025, and there's a system called Flamingo, and it has 156 qubits, and here it goes to about in 2029 to about 200 qubits, and it goes in 2023 goes to about 2,000 qubits. That's kind of the systems that we're talking about at the moment, the kind of quantum systems that we can realize at the moment. But these are physical qubits, and physical qubits are very noisy. And in order to make a quantum computer, you need reliable qubits, and you need an error correction scheme that currently requires on the order of 100 physical qubits to make one logical qubit. So you have to divide these numbers by roughly a factor 100, and therefore we have still very small quantum computers to do anything impressive at the moment. So this is for what is called fault-tolerant quantum computing, and you need a fault-tolerant quantum computer in order to realize Shor's algorithm, for instance, and we're not yet there. But in the meantime, there's something called NISQ computing, which is, I always forget, noisy intermediate scale quantum. This is basically the philosophy. We have these wonderful quantum devices. Is there some low-hanging fruit that we can already do now without a fault-tolerant quantum computer in order to show already quantum advantage over classical algorithms? And then you should think about algorithms such as optimization algorithms. So here I give some examples of these kind of NISQ approaches. And it's basically, they are all about preparing a quantum state. And so you can think of, as I will show in a minute, you have a quantum circuit, you have an initial state that you can easily prepare, and then there is a state that you want to prepare through this quantum circuit. And this state that you want to prepare can do various things. Examples are represent the ground state of a complex molecule, right? So if you can do that, then you know from that ground state that you have computed of this complex molecule, which is a ground state of a quantum Hamiltonian, then from that you can infer interesting properties about the electron structure in that molecule, which gives you insight into the chemical properties of this molecule, and can be helpful in drug design, in material design, etc. Other very related is solving complex optimization problems. So like a traveling salesman problem. You can make a Hamiltonian again such that the ground state of the Hamiltonian represents the solution to your traveling salesman problem. And so your quantum circuit will go from an initial state to a final state, which is the ground state of that system. Okay, so and the quantum computing is that evolution process. And sample from a complex distribution, as I started out in the beginning. So I want to talk about that quantum state preparation problem. And the traditional way that is done is in a quantum circuit. And this circuit is, so you see these nodes, these zeros, this is 4 qubits. They are prepared in the 0 state. So these, there's zero of the sigma z operator for those who know about that. And so it's some easily preparable state. And then we have some gates. So you have a rotation on single qubits in the z, x, and z direction. These are single qubit operations. Then you have some mixing. And then you have, again, some single qubit operations, some mixing. You do that a while. And then you get an end state, which is psi. And it is written as u times o. The o is the initial state. And the u is the whole quantum circuit. That is being that operation, right? And it is this end state, psi, is parameterized by theta, and theta are all these angles that you can twist and tweak. And now you want to optimize what is called some Hamiltonian. So this Hamiltonian is maybe encoding your traveling salesman problem. And you want to find the minimum of this expectation value. That is the vector, that is the ground state of this Hamiltonian. And okay, so you run this circuit with a random initialization of theta, you get some end state, and then you can measure this quantity, this numerator of this thing that you want to optimize, this psi dagger h psi, you can measure it by repeated measurement. The Hamiltonian breaks down in a sum of small terms. You measure all the small terms, you add them by repeated measurement, you measure 10,000 times, and then you get an estimate of that number. And you can also get estimates of the gradient. I'm not going to go into detail about that, but you can basically do gradient descent then on this quantity and find the parameters that best solve this. And this is a current approach, main approach to optimize quantum circuits. And it's known as a variational quantum algorithms, or the variational quantum eigensolver. Now, one of the problems that is faced in this optimization are so-called barren plateaus. And this is a funny phenomena that I didn't know from classical optimization in neural networks where we have local minima. This is different. This is a cost function that is everywhere flat except around the minimum. So it's like a golf course with a little hole in it. This is the problem that wherever you initialize, your gradient is zero. And the gradient is vanishing exponentially in problem size. And the size of the pit, the well, is also decreasing in system size. So here you see blue is a small system, orange is a larger system. So it gets worse and worse. So it's really sort of a showstopper. Okay, so, but now the idea is that if you add noise, then it will improve the convergence. And this is something we know, of course, very well from simulated annealing and from all kinds of optimization problems. If you add noise, it gets a little bit easier. And here you see an example, not any noise, but there's a recent paper, energy dissipation to mitigate barren plateaus. So engineered dissipation, so dissipation is noise. Engineered is that you need a certain kind of noise, and you can make certain noise that will improve the convergence. Here is a simple illustration of computing the ground state of this hydrogen atom at a certain atomic distance. You want to minimize that Hamiltonian, and you see that basically if you just add any noise, then you get the blue line. It doesn't work. If you do the unitary, which is the standard approach, you get the red line. If you combine these two in a smart way, you get the green line, and you get below this threshold, and this threshold is what is known as the chemical accuracy. If you get below that, the results become significant for chemists. Okay, so this is one idea that I want to exploit. Now, the second idea is to replace this discrete circuit by an analog computation. So instead of having the circuit with these fixed gates, you can say, okay, well, I'm just going to run the Schrödinger equation itself in continuous time. So I have the Schrödinger equation. For those who've never seen it, it's that thing over there. It's a first order linear differential equation where psi is a wave factor. Is a wave factor, you can think of it as if you have n bits, it's a vector of length 2 to the n, and it's made up of, it's living in a complex place, complex number. So it's a vector of complex numbers, okay? So you have 3 qubits, then you have an 8-dimensional vector. And H is then 8 by 8 matrix. And so you get this evolution equation. You start with the initial state, you run this linear system, you get a final state, and now you can change the Hamiltonian by having, so you say the Hamiltonian typically gives 2 terms. One is the sort of part of the Hamiltonian that you cannot change. These qubits, they interact in a certain way and you cannot change that, but you can influence them individually. So you have this second term where the UKs are the ways that are the controls that you apply to this system. And so then the picture is that your control solution is sort of a continuous, this is U for controls from over the whole time period. And this is then your solution. And there is recent papers that show that for this optimization of these chemical problems that you get, for instance, from 9 nanosecond a time, what normally took on the digital circuit 500 to 800 nanoseconds can now be reduced to about 9 nanoseconds. And on 4 qubits, you get from say basically, well, 50,000 something, it reduces to 4,000, 40 nanoseconds. And to give you an idea, the decoherent times on these modern quantum computers, they are on the order of 70,000 nanoseconds. So this is quite relevant, right? I mean, these are small problems, but you can really make them much faster because, of course, you have to remember that if you do this quantum computation, you have to do that in a time which is shorter than the decoherence time of the physical device, because after that you lose your quantumness and you might as well use your standard PC, right? So this you need to be fast. So this is very, very relevant. So this is setting the stage for, okay, so and this is then one of these examples of systems that you can use this for. This is a company called QERA, and this is one of their so-called neutral atom processors, where they can have hundreds of these neutral atoms in arrays that are held fixed in space by laser lights that put a sort of a periodic grid there where these atoms are there and they're at a certain distance from each other, and they can be influenced individual, and you can do quantum computation on such a grid of these atoms. And so, okay, that's the kind of thing that I'm talking about. So what I tell you, my approach is that is to use stochastic optimal control for analog open quantum systems. So analog I explained to you, that's continuous time. Open I haven't explained to you. Open means that a quantum system is in contact with its environment. The Schrödinger equation that I showed to you is a closed quantum system, and it's but there's noise, and I will talk about that. So analog yields shorter circuits, I showed you, and stochasticity yield better optimization. Now I will show you that these open quantum systems can be described by what are called unravelings. These are stochastic differential equations that simulate this open quantum system. We'll get to that. And then at the end, we will be able to set up this control of an open quantum system as a stochastic optimal control problem of a particular type. And then there is a subclass of those problems that is of the form of the path integral form, and I can solve it with these path integral methods. And that's essentially the story today. So if you have any questions, please jump at it and tell me, otherwise I will just go through. Okay, so the outline is I tell you about open quantum systems and unravelings. I tell you about stochastic optimal control, path integrals, which I also told you about last week, and then I put it together. Okay, so I added a few slides because I assume that not everybody is aware of the quantum world. So unitary evolution Schrödinger equation is basically you have this wave vector, this complex vector, and it has a norm of 1, and you do a unitary evolution on this where H is a Hermitian operator. So this will make a rotation in this complex space that preserves the norm. So think of the state space as a big ball in the complex sphere, and you have a vector, and your unitary is just moving it somewhere else. That's what's happening. Okay, so this is linear and deterministic. That's what it does. Okay, but now we have this system embedded in a larger space, right? So there's this, we have our small quantum device, but we have a big world. And actually the whole world is quantum. We tend to forget about that, but it's really quantum, you know. And so if you have a small isolated quantum system, it has influences from the environment. The influence of the coupling of the system with the environment is very, very complex. If you have a sort of a statistical physics background, well, you just add noise and sort of a Gibbs distribution and blah, blah, blah. In the quantum case, it's much more integrated, much more complex. But there is that influence. So I draw this little picture here. So if I have an electron which is approaching a photographic plate, it will come somewhere on the plate and make a spot. The quantum theory will tell you, the theory of the closed quantum system, the Schrödinger equation, will tell you this red line. It will give you the probability where this electron will end up on the screen. It doesn't tell you where it will end. It gives you the probability. That means that if you repeat this 100 times, you will indeed find that probability distribution. So the quantum mechanics gives you an ensemble description, but it doesn't give you the individual event. It is thought that the individual events come somehow from the environment, and the way it's coupled to the environment. Okay, so in order to get you to that, I have to introduce for you something which is called the density matrix. So we have the Schrödinger equation on the top, and now so think of it as a vector. Now I write it as a column vector times a row vector. I make a rank 1 matrix. That's called rho. And I can, just plugging that in top, I get this equation for rho. I haven't done anything, right? Okay, so I have now rho. Rho is called a pure state because it's of this form psi bar. It's just one thing. Now, when you couple it to the environment, rho will become a higher ranked matrix. It will fill up. So what happens? So suppose we have two particles that can be in both in two states. So the first particle can be in the state black and white, and the second particle can also be in the state black and white. And we can prepare the system to be, if the first particle is in the white state, the second particle is also in the white state. Or if the first particle is in the black state, the second particle is also in the black state. So they're correlated. Their colors are completely correlated, okay? This is the way you have that. Yeah, the system is in a pure state. We can make a density matrix, which is as before. And the total system is in a pure state. Now I can do something. I can say, okay, well, I have a two-state system, but I'm only interested in one of the subsystems. So one of the subsystems is going to be our quantum computer. The rest is going to be the rest of the universe, okay? So I have two systems, and then I look only at system one. This is rho one. Now, rho one is the average over everything that system two can do, right? So that is you trace out all the degrees of freedom of system two. And what will happen is that it will be 50% of the time, it will be in state white, and 50% it will be in the pure state black. You have lost the correlation between system one and two. But the point I want to make here is that now this is in a mixed state. So it's not, so here rho is a pure state. There's some vector that it is the outer product of. Here, no. It's a mixture of two pure states, right? And it's itself not a pure state. Okay, it's a mixed state. And these mixed states arise, they describe systems in their interaction with the environment. So here, once again, so here I have a pure state psi1 and a pure state psi2, and I can make a pure state psi, which is a linear combination of these two, okay? And then I can make a density matrix, which is pure. I can also say take two states and make a mixture, psi1, psi2, okay? That's a mixed state, different things. Okay, so the way that the systems interact with the environment is in the simplest description. It is a very complex story, but the simplest way to do it is a so-called Markovian description. You can appreciate that. So you have a system evolving over time. You have the environment evolving over time. Now, if you trace out the environment and your system itself, your system plus environment is a Markovian, you trace out the environment, your system is no longer going to be Markovian, right? Because you get all these long time correlate by integrating out the whole environment, you get all kind of old-time couplings. But there is certain limits in which a Markov description is still valid. And that is in the case in which the coupling is not too strong between system and environment, and in which the environment is very, very big. That basically means that the change in the state, in the system, does not really affect the environment, because the environment is so big that it's basically being absorbed. So it stays in the same state. So under these two assumptions, you get a Markov description of the system in interaction with the environment. And this is it. So it is rho dot, that's the time derivative of rho. We see the first part I already showed to you, that was the unitary part, that comes from the Schrödinger equation. And then you have all this other mess there, that comes from the coupling with the environment. And there's a sum over repeated indices, K and L. So these are a bunch of, and C, CK are operators. And this thing between curly bracket is the anti-commutator. It's the first argument times the second argument plus the second argument times the first argument, just anti-commutator. And so this is a linear equation in rho, right? It's a linear in rho. And it describes the unitary part and the part that is coupling to the environment. These C's, so for instance, in the case of a single qubit, this C can be a measurement. So you can measure the system. That will be one way to interact with the system. In which case these C's are Hermitian operators. Or it could be a dissipation operator, such as a sigma plus or sigma minus operator. Sigma plus would be something like, it would be something like a matrix like this, something that forces the state always to be in this lower state. Okay, so this is a description that you get by tracing out the environment for the open quantum system. Now, you can make a stochastic description of that, and that is the so-called unravelings. So the way you think, the way that I best explain this expression, this horrible expression, the first term we already know because it's the Schrödinger equation, right? That's just our Schrödinger equation. And then look at the red term. It's just the coupling of one of these operators C to the wave function times the noise term. The psi is a white noise, real. Let's say it's real. We can take it real. Okay. So this is the way that. So we have deterministic evolution under the unitary, which is the first term, and then we have this stochastic evolution with this funny white noise thing. And all the other black terms that are there are just there to ensure that the norm of the wave function doesn't change over time. This is the summary of that thing. You know, you just do that and you make sure that in the limit delta t going to 0 in the lower. Okay, so then you get, so the norm is conserved. So that's the equation that you get. And what this means is that if you now define psi dagger as from there, and you take the expectation of that thing with respect to that noise that you have there, and you look at the evolution of that thing, then the evolution of this thing is exactly the Lindblad equation. So this is, so if you think about Fokker-Planck equation, which is a diffusion of, say, a Gaussian, you can simulate Fokker-Planck equation by just a Brownian motion. And if you have the average of the Brownian motion, it gives you the Fokker-Planck equation. In this way, the same way, the average of this top equation gives you this Lindblad equation. Okay? This is the unraveling. Okay, so we have a stochastic dynamics, so we can do stochastic optimal control theory. This is maybe, I have 10 more minutes, okay. This is really sort of interesting for, you know, those of you who are interested in a measurement problem. Here I have a single qubit and I do a measurement on a single qubit. So I have the unitary part of the evolution. I take 0 for the simplest case. I just have one measurement, so C is sigma z. This is the measurement of sigma z. I may measure whether the spin is up or down in the sigma z direction. And if I look at the Lindblad equation, it reduces to this equation there. Rho dot is sigma z times rho times sigma z minus rho. Okay, that's the equation what it is. If I look at the unraveling, I get this equation there. And that with mz is, oh, I should have pointed out. This is one thing that I forgot to point out. So here in this equation, there is the c's, the big c's, which are these operators. They don't depend on psi, but there's also the small c. And the small c is the expectation value of the Hermitian part of that operator. You don't have to understand about that, but what you have to notice is that it's quadratic in psi. So that means that this equation is nonlinear. It's a nonlinear equation. Very, very important. Okay? No longer linear. And here we get the same. So this m is basically that small c that I had before, and it's that expectation value. And this equation for psi implies an equation for m, and it's of this form. And you see that it's something nonlinear that multiplies the noise. And you see, if you know a little bit about that, so if m is plus or minus 1, the noise is 0. If m is 0, the noise is maximal. So if you take the expectation value of dm, it's 0, right? Because d psi is 0. But there is a state-dependent noise. And that means that in areas where the noise is large, the system is pushed away. And the system, in the areas where the noise is small, is going to be attracted, right? So if you have, so the way I always picture that, so if you say that the noise increases in this direction, then if you are here, you have large noise, so you make large steps here. But if you're here, you have small noise, you will make a small noise there. So in effect, there will be a drift in that direction, pushing you to the areas of small noise. Areas of small noise are plus or minus 1, m is plus or minus 1. So you see that this system is going to one of the eigenvalues of the sigma z operator. And this is the measurement outcome. If you remember the measurement outcome of your quantum mechanics maybe, you measure sigma z, you get as output one of the eigenvalues. You see this is right, this equation is 0 when the state vector is one of the eigenvectors of that operator. So this is illustrating this theory a little bit. Okay. So now the optimal control, part 2 of the lecture. Okay, so this I did last week, so I hope that you got a little bit of that. So we have a stochastic system, we have a Bellman equation. So we know all about that. I told you all about last week, so we can be very, very brief about that. Now let's take, so now I also told you that if you have a very simple example, if you take this system where you have a control and you have a noise, you can compute the solution of the Bellman equation. It will be given by a heat map of this form, where this is the optimal cost to go, J, as a function of time and space. And the control is basically the gradient of that. And so you have this anticipated potential that I talked about last week. The potential here time 2, but at the anticipated times you have other potentials, and the control is essentially the gradient of that quantity, of that optimal cost to go. And so you see that the particle steers to the middle around here, because yellow is lower than red. But then at some point it will have to make a choice. There's a instability created, and it will have to go to plus or minus 1, which is the target cost where it wants to go. And these are trajectories under optimal control. Now, in the case of the path integral formulation, you have, if the dynamics of this particular form, that the control and the noise appear in the same channel, where G and F are arbitrary nonlinear functions, and if in addition that the control cost is of the form of a state-dependent part, which is a V and psi, end cost and state cost, path cost, but that the control-dependent part is quadratic, then you can show that the Bellman solution, the Bellman equation, can be solved using this path integral description. So you get essentially that the optimal cost to go is minus lambda times the log of the expectation of e to the minus SUT, where SUT is that quantity over there, evaluated under a control U. And the control U is here giving the value of the trajectories, right? So it depends, the trajectories are generated. This expectation value sub U means that you compute the expectation value of this quantity over trajectories that are generated with control U. And the optimal control is similar, given by this formula. Okay, so that means that you can, for these path integral methods, you can obtain the optimal control by sampling. And that's an advantage, and that we want to exploit here. So here you see the same problem again, but now solved by the path integral method. You take this same dynamics. We have the cost to go to one of these 2 points, plus or minus 1, which are indicated here by the stars here in this figure. And you see where this works? Yeah. And so the way that you compute the solution is that you solve this, and you can use here any type of control, the sampling control. So for instance, you can use U is 0, and then this is 0, and then the end cost is just this phi, and this is the noise. And so you sample this, and you sample this everywhere, and you get this heat map again, and you take the gradient, and it gives you the optimal control. And so this is how you can visualize how you compute these values, is that you start sampling and you get these trajectories and you color them with this color, e to the minus phi over nu. And if phi is very small, you get very big colors, and if black colors, and if phi is very large, you are very bad, you're very far off target, you get gray colors. And so this bunch of weights gives you basically the optimal cost to go. So this is in a nutshell what this path integral method does. So this doesn't work. Well, this has been used in many applications in robotics, and maybe if some of you have seen this video. This is sort of a real-time control using this method. It's running it's running at a high frequency, so 60 hertz. In 60 hertz, you get all these trajectories, and these trajectories are used to compute the optimal control at that point, and then these are passed to the motors, and then the time step is made, and then the whole thing is done again. Yeah. Okay, so this is a method that is nonlinear. It is real times fast. It is stochastic. It's very robust, and so maybe it's also good for quantum computing. So that's the point. So now I have 3 minutes left, and I have a dilemma because I can tell you about importance sampling, or I can tell you about the application on quantum systems. Very briefly, you can sample with different controls. As I said, as you know, can control 0 or any other control. But it turns out that the quality of the sampling depends very much on the quality of the control that you use for the sampling. So there's a sort of a bootstrapping problem. All these controls are in expectation, are they unbiased? So they are all correct asymptotically, but their variance differs enormously. And in particularly, the better the control in the terms of optimal control, the better this control is also for sampling. And the optimal control for sampling is the optimal control, is a solution of the optimal control problem, essentially. So you get this bootstrapping problem. So the way that suggests an algorithm is that you start with 0 control as an initial guess or any other guess. You generate samples, you compute the control, which is hopefully better. You start sampling with that, and then you iterate. So this is this iterative importance sampling. Okay, so you can, if you have a parameterized model given by some parameters theta, you can then optimize these parameters from one batch of for all the controls for all states, state and time, from one batch of samples that you draw. Let me leave it at that. Okay, so now we get the control of our quantum system. So we have the Lindblad equation, and we now have a control cost, which is that at the end we want to minimize some G, some Hamiltonian, where G is the target Hamiltonian. This can represent our traveling salesman problem or our quantum chemistry problem or whatever. And we add this quadratic control cost to it. And we solve it in terms of the stochastic problem, where we use the unraveling of the Lindblad equation to get this equation. And so whereas the first problem is a deterministic problem in rho, here we now get a stochastic problem, which is the same problem essentially. And here you see the solution, how we do this on a single qubit. So one qubit has a wave function, which is a two-dimensional complex vector. Can be, because of normalization, can be parameterized by 3 real numbers. And since it's not one, it lives on the sphere, right? That's the wave function. And here you see trajectories going from x to y. And your control, the control actually in this case has only sigma x and sigma y rotations. Now, sigma x rotation is a rotation around the sigma x axis, sigma y is around the sigma y axis. What you would need to go from x to y is actually a rotation around the sigma z axis, but sigma z is not one of our control primitives, so we don't have that. So you need a smart combination of sigma x and sigma y to do this. This is an open loop control, so you see the trajectories diverging, and why? This is a whole story there, because closed loop control would mean that you get state feedback information, right? But a quantum system, once you measure it, it collapses to a state. The state is gone. So the measurement problem in quantum, so quantum feedback control is it's a completely different story. I have ideas about that, but I will not talk about it today. So, and in the industry, most people are focusing on open loop control at the moment. So I'm also focusing on that at the moment. So here you see the final control solution that we get. This is the controls on X and Y over time. And here you see the control cost going down. That is the black one. You see the fidelity. This is the quality, the overlap with the target state that you want to reach, this Y state. Both the mean, which is the blue one, as the worst case, which is the red one. And here you see the effective sample size of the sampling. So how good is the sampling going? You see that it doesn't go to 100%. It goes to about 20%. And that's because we're not using a feedback controller. We're using an open loop controller. So this is a single qubit. Here is an example. Well, it's much better than other methods, but I will have no time to talk about it. So here we also did it for 4 qubits, and we can get basically current methods get to about 10 to the minus 2, 10 to the minus 3 accuracy in fidelity. That is 1 minus the fidelity, fidelity being the overlap, which is maximally 1. So it has to be something as small as good. So they get 10 to the minus 3. We can get up to 10 to the minus 10, basically. And these are the kind of controls that we make. You see, this is the annealing schedule in D, but you see the controls. These controls are really ugly. They are really, really nasty because you have all these non-commuting variables, and they really, you would think that you get something smooth and something beautiful out, but you get really, really something ugly out. Anyway, so that's very short. I'm running over time, so I don't want to abuse your time. This is some benchmarks that we did on quantum chemistry. So this is, on the left, this is a quantum chemistry problem with 4 qubits. So these quantum chemistry problems are mapped onto qubits. There's also a whole story there, but then you get a qubit optimization problem. PQE is the digital circuit solution. Horizontal, you see the distance of the elements, and it's different quantum problems. So these are different quantum problems. And here you see our methods in red, mean and best, and that is the standard method, mean and best. And here on another problem, which is larger, basically, we both find, everybody finds good, we find both good solutions. So what we still have to do is whether we can actually optimize the time, get also much shorter circuits as we wanted in the other, as it was reported in the other paper. Okay, let me finalize. Yeah, I have no time to talk about it. So you can do this on a quantum machine also. So I did this now in software, but of course, in order to get real speed up, you have to do it on a quantum device because my computation in the computer is, of course, also exponentially limited. You can do it in a quantum device, but I'm looking for partners to do that. Summary. Analog quantum computing is promising alternative for digital quantum circuits. Shorter circuit times, open quantum system approach is promising to mitigate barren plateaus. The new control framework for open analog quantum systems based on unravelings and path integral control provides quadratic speed up. Quadratic means that you work with the wave function, which is 2 to the nth, instead of the density matrix, which is 2 to the nth times 2 to the n. So you get a quadratic speed up there. Exploits quantum noise sweet spot. So that means that you want to add noise to get better optimization, but you don't want to add too much noise because then you lose the quantumness, right? So there's a trade-off there. We're outperforming the intermittent control methods, and it is scalable on quantum computers. I think it's the first method that can do this. And this is some future work. So we're going to apply this on real hardware. We have a method to parallelize this on digital machines. And there is something called tensor networks, which is a way to break down the wave function in sort of components, where you can, of course, where you can then break this 2 to the nth scaling problem of the size of the wave function. You can get it as a product of simpler things, and that's also work in progress. I hope that I've given you a little bit of a flavor of this kind of work. It's very different from the classical world. It's also very, very difficult to say. I engaged in this in 2018 with the hope to make some fast advantages, but it turns out that everything you think of has already been done, and everything you have knew that is probably close to impossible. So this is a very, very, very challenging field, but still a lot of fun. And thank you for your attention. Bye.